Welcome to this video on artificial intelligence with Python. This is an internship video covering key concepts in AI and machine learning. Here are some of the key abbreviations you will encounter. AI for artificial intelligence, ML for machine learning, NN for neural network, IP for image processing, CNN for convolutional neural network, DL for deep learning, DNN for deep neural network, and ANN for artificial neural network. We can draw a parallel between artificial intelligence and the human brain. AI and machine learning aim to mimic the functions of the human brain, which is the ultimate example of an intelligent system. The various human organs can be mapped to AI tools. For instance, the eye is like a camera, the nose is like a sensor, and the ear acts like a microphone for speech recognition. Hands and legs relate to motors in robotics, and emotions are comparable to software. Let's cover the basics of AI. John McCarthy is known as the father of artificial intelligence. AI involves making intelligent machines, robots, or software capable of thinking intelligently, similar to humans. This is achieved by studying how the human brain learns and solves problems. What is machine learning? It's an application of AI that allows systems to automatically learn and improve from experience without being explicitly programmed. It converts an ordinary system into one that learns, predicts, and improves. This diagram provides a quick overview of what AI is and its various subfields, including machine learning, deep learning, computer vision, and natural language processing. Machine learning techniques include supervised, unsupervised, and reinforcement learning. Key concepts in AI include machine learning, natural language processing using the NLTK package, speech recognition, heuristic search, gaming, neural networks, genetic algorithms, computer vision, deep learning, and robotics. Humans excel in emotions and complex thinking, performing diverse activities with external organs. Machines, like a JCB, are good at heavy tasks, such as lifting 1,000 kilograms. AI-powered machines combine these abilities, integrating elements like cameras, sensors, and software for intelligent operation. The goal of AI is to create systems that can function intelligently and independently. This mirrors human actions, such as speaking and listening through speech recognition, reading and writing via NLP, and visual tasks using computer vision. Movement is achieved through robotics, and recognizing patterns is done through pattern recognition or machine learning. The human brain's network of neurons is analogous to an artificial neural network. For more complex and deeper processing, we use deep learning or deep neural networks, which are modeled on how the brain processes information, such as visual streams. As key takeaways, ML, IP, NN, CNN, DS, and DL are all part of the broader field of AI. For AI or machine learning to function, data is essential to train the algorithms. Commonly used integrated development environments, or IDEs, for AI and Python development include the Anaconda platform, Jupyter Notebook, IDLE IDE, and PyCharm. To work with AI in Python, you will need to install several useful packages. The installation commands typically use pip and include packages like numpy, scipy, matplotlib, sklern, pandas, sys, keras, and tensorflow. After installation, you can test if the packages are correctly installed by importing them within your Python environment, as shown in this Python shell window. NumPy, short for numeric Python, is an open-source library in Python. It's crucial for mathematical, scientific, engineering, and data science programming, especially for multidimensional arrays and matrix multiplication. It's also known for its memory efficiency. TensorFlow, developed by Google and open source, offers excellent community support and is highly parallel. It uses various back-end software like GPUs and ASICs. It allows for monitoring model training and tracking metrics, offering industry-leading performance. Key tensor types are TF variable, TF.constant, TF.placeholder, and TF sparse tensor. AI can be broadly classified into two types. Symbolic-based AI includes computer vision, image processing, and robotics. Machine learning, on the other hand, is data-driven, allowing machines to learn patterns from vast amounts of data for tasks like classification and prediction. Machine learning is a subfield of computer science and an application of AI. It gives computer systems the ability to learn from data and improve without explicit programming. The main goal is autonomous learning without human intervention, achieved by recognizing patterns in data examples or experiences. The various algorithms in machine learning include linear regression, logistic regression, neural networks, decision trees, naive Bayes, clustering, and support vector machines. Machine learning uses different types of input data, such as Excel data containing numbers and strings, various formats of images or videos, and audio signals. Machine learning algorithms are categorized into three main types: supervised, unsupervised, and reinforcement learning algorithms. AI itself is built from complex algorithms rooted in mathematical domains like algebra, calculus, probability, and statistics. Supervised machine learning is the most commonly used type. The learning process is analogous to a teacher supervising the process, where possible outcomes are known, and the training data is labeled with correct answers. Supervised learning problems are divided into two categories. Classification problems deal with categorized outputs such as, quote, black or non-teaching. Regression problems involve real value outputs like distance or kilogram. This image illustrates a supervised classification problem. We input various fruits and the system learns to classify them, demonstrating the training process and the goal of classifying based on learned features. This image shows a supervised regression problem. The system predicts house prices based on various input features, like the number of rooms and size, aiming for a continuous, real-valued output. Regression, a vital statistical and machine learning tool, involves parametric techniques for making predictions based on data. It establishes a relationship where continuous output variables depend on input variables. Regression is used for predicting values such as prices or economic variations. Examples of supervised machine learning algorithms include Gaussian naive Bayes, support vector machines (SVM), logistic regression, random forest classifier, and k-nearest neighbors (KNN) classifier. Unsupervised machine learning algorithms lack a supervisor or labeled training data. They aim to discover patterns in data without explicit guidance. This type of learning is closely aligned with true artificial intelligence. Unsupervised learning problems fall into two categories. Clustering involves discovering inherent groupings in data based on similarity, like grouping customers by purchasing behavior. Association problems focus on discovering rules that describe large portions of data, such as finding customers who buy both X and Y. This image illustrates unsupervised learning, where the algorithm is presented with various animals and must autonomously group them into clusters based on shared features without prior labels. Another illustration of unsupervised learning shows the clustering process. Data points are naturally grouped into distinct clusters by the algorithm, revealing inherent structures in the unlabeled data. Examples of unsupervised machine learning algorithms include k-means clustering, which is widely used, and mean shift clustering. Reinforcement machine learning algorithms are less commonly used. They train systems to make specific decisions by exposing the machine to an environment where it continually learns through trial and error, capturing the best knowledge from past experiences to make accurate decisions. Markov decision process is one example. This image visually represents the process of reinforcement learning, where an agent learns an optimal sequence of actions within an environment to maximize cumulative reward. This block diagram summarizes the core components of the reinforcement learning process, showing the interaction between the agent, the environment, and the reward system. This image illustrates the use of reinforcement learning in applications such as self-driving cars, where the vehicle continuously learns and adapts its driving decisions based on environmental feedback. This block diagram outlines a typical AI workflow. It starts with a dataset, which is processed by the algorithm using Python and libraries like OpenCV and scikit-learn on a laptop, leading to a predicted output, such as loan available or not. The methodology for a machine learning project includes several key steps: inputting data, importing necessary libraries, visualizing the dataset, pre-processing the data, feature extraction, splitting data for training and testing, performing machine learning analysis, and finally, generating the output prediction. Dataset analysis is crucial. Columns are referred to as features or attributes. You must check for balanced or imbalanced data and identify the output class. Key steps include checking parameter value counts, handling empty cells by filling with average values or removal, removing imbalanced data, and deleting unwanted columns. Pre-processing the data is essential because machine learning requires data to be in a formatted, meaningful way to start the training process. This converts raw data into a usable input format for the algorithms. Pre-processing steps involve importing useful packages, gathering example datasets, and transforming data through binarization, mean removal, scaling, normalization, and labeling, before finally splitting into train and test data. When a computer processes an image, it reads it as an array of pixel values. For example, a 480 by 480 color image is represented as a 480 by 480 x 3 array of numbers, where each number from 0 to 255 describes the pixel intensity. Image feature extraction identifies key characteristics from an image that are useful for prediction. These features include color, pixel intensity, shape, and texture. This diagram illustrates how an algorithm processes an image. It highlights the transformation of raw pixel data through various layers of processing to extract features and ultimately classify or identify objects within the image.